DC motors are often used in industrial applications that require precise speeds and constant torque as the load on the motor varies. Traditional electromechanical control methods can be used in these situations, but solid-state DC control methods provide a more accurate way to control the motor. And when industrial processes that use DC motors must be integrated with other modern control systems, solid-state DC controls are a necessity. Regulating or changing the speed and torque of a DC motor is done by controlling the level of voltage applied to the motor. Raising the voltage lets the motor draw more current, which increases the speed or the torque. If the applied voltage is lowered, the motor cannot draw as much current, and it slows down or it produces less torque, or both. The most common method of producing the variable voltage required to control the motor is to change or rectify AC voltage into clip pulses of DC. The pulses are larger when more voltage is required, smaller when less voltage is required. All solid-state DC controllers monitor feedback from the motor in order to accurately determine the voltage required at the motor. To understand how a solid-state DC motor control system works, let's look at the basic components of a typical system. The motor, which produces the mechanical force that drives a load, and the controller, which regulates the electrical power going to the motor. Most DC motors operate on the same basic principle. They have armature windings on a rotor that turns through a stationary magnetic field. Applying voltage to the motor creates a stable magnetic field in field windings. As current flows into the armature through the brushes and the commutator bar, it is continually reversed or commutated and causes the armature to spin. If the voltage is increased, the armature will spin faster and with more force. Now, not all DC motor windings are connected in the same way. Series motors have field windings wired in series with the armature windings. Shunt motors have their fields wired in parallel with the armature. Compound motors have two field windings, one in series with the armature, the other in parallel. Separately excited motors have field windings powered by a source separate from the armature. Other DC motors use a permanent magnet for the field. These are commonly called PM motors. The important thing to remember about these differences is that not all controllers can be used with all types of motors. However, most solid-state controllers will operate both separately excited and PM motors. The basic function of the controller is to regulate the speed and torque of a motor. All controllers have two major sections: a power section, which produces the voltage and current that runs the motor, and a control section which regulates the output of the power section. When a DC controller is supplied by an AC electrical system, the first job of the controller's power section is to convert AC into DC. This is usually done with a full-wave rectifier, or full-wave bridge, which converts both the upper and lower halves of the rising and falling AC sine wave, the full wave, into pulses of DC current. When the incoming AC current is single phase, the resulting rectified current is not continuous, but pulses on and off. For smaller motors, this intermittent current usually works fine. Large motors, however, typically those drawing more than about 50 amps, cannot adequately commutate or reverse high amperage intermittent current. For this reason, larger motors are generally fed with three-phase current. Rectifying three-phase AC provides the motor with a steady, almost continuous supply of current. When current to a motor is rectified, it is clipped into pulses with solid-state switches, typically SCRs, or power transistors. These devices are turned on or triggered by signals from a gating circuit in the control section. They are turned off when current in each phase drops back to zero, or when the gating signal is removed. The speed and torque of the motor depend upon exactly when, during each AC cycle, these devices switch the current on. The sooner they switch on, the wider each pulse of DC will become. To select a particular motor speed, an operator turns a potentiometer or sets the speed on a controller's keypad. To maintain that speed, the controller adjusts the trigger in response to changes in motor speed. If the load is suddenly decreased, the motor tries to speed up. This causes the gating circuit to retard the trigger point. In other words, to shift the trigger point so it includes less of each pulse. Less power is transmitted to the motor. If the load is increased suddenly, the motor tries to slow down. This advances the gating circuit, and the trigger point shifts to include more of each pulse. More power is transmitted to the motor. These adjustments of the trigger point occur quickly enough that motor speed can be kept virtually constant, or it can be changed almost instantly. Correct gating requires accurate monitoring of the motor's speed. This can be done in several ways. One method is to monitor back EMF, the voltage a DC motor produces as it turns. The strength of the back EMF generated by the motor decreases as the motor slows down. The controller senses the decrease in back EMF and compensates for the slowdown by advancing the gate to shift the trigger point so more of each pulse gets to the motor. Or if the motor tries to speed up, back EMF rises and the controller retards the gate, shifting the trigger point to include less of each pulse. Another method of controlling gating is to monitor motor speed by using a feedback device mounted directly on the shaft. For example, the controller can detect very small changes in the voltage output of a tachometer or a resolver attached to the motor shaft. Then use that feedback to determine how much to adjust the gate and shift the trigger point. Or magnetic pickups or encoders can provide the necessary feedback. These devices produce pulses of current as the shaft rotates. The interval between pulses, or the number of pulses in a given time, can be used to adjust the gating circuit and the trigger point. Many feedback devices will also indicate the position and the direction of rotation of the motor shaft in order to place loads at precise locations. To regulate speed and torque during operation, the controller normally varies voltage to the motor's armature. Armature voltage is raised or lowered, and field strength is held constant, at least up to the motor's base speed, its speed at rated voltage and load. To operate a motor above base speed, the field voltage is lowered, weakening the magnetic strength of the field. When this happens, the armature can draw more current, and the motor can speed up. A DC motor's maximum speed and torque are limited. If the motor draws too much current for too long a time, it will overheat, damaging the insulation in its windings. The maximum continuous current the motor should draw is called the motor's current limit, or torque limit. For short periods of time, DC motors can draw 150 to 200% of this current. However, to prevent damage to the motor when it draws higher than normal current, all solid-state DC control systems include a current limit circuit. If the motor draws excessive current because it is accelerated too rapidly or because the load demands too much torque, the current limit circuit will override speed regulation and prevent the motor from drawing excess current. This current or torque limit is set based on the application. Setting the limit too high, or allowing the motor to operate in current limit too often, may cause excessive sparking in the motor, will wear out the brushes much faster, and may eventually damage the commutator as well as the motor windings. Now, in some applications, regulating torque is more important than regulating speed. Many controllers can be modified to do this by installing a wire jumper between terminals on the controller, by flipping a switch, or by changing the programming. When regulating the torque of a motor, maximum speed must be limited to prevent the motor from overspeeding. This is done with a speed limit circuit that is preset based on the application. How accurately the controller can maintain the speed or torque of a motor is called its regulation. Usually, regulation is stated as a percentage of its rated or base speed. Many solid-state systems can achieve speed regulation of a few hundredths of a percent, even when the load varies from no load to full load. The regulation provided by the controller at any given moment depends on how fast the speed or torque must change. If the speed or the load changes too quickly, precise regulation may be lost. To prevent this, the controller ramps the motor up and down. That is, it accelerates and decelerates the motor at a particular preset rate, depending on the application. Besides the basic functions of rectifying current, adjusting the trigger point, and monitoring the motor to regulate its speed and torque, most solid-state DC controllers perform many other functions as well. Many DC drives provide either dynamic or regenerative braking. In dynamic braking, the electrical energy generated by the spinning armature when power to the motor is turned off is fed back to resistors. This energy is dissipated as heat. In regenerative braking, the electrical energy is fed back into the AC line, where it may help supply electrical power for other motors or processes. While some drives can provide regenerative braking in one direction only, many large drives are designed to provide it in either direction. To do this, they have two separate bridge rectifiers, either of which can supply power to the motor or feed braking energy back into the AC line. Drives with dual bridges are capable of four-quadrant operation. This means they can run and brake in forward and reverse. One bridge is used to operate the motor in forward and to brake a load when the motor is operating in reverse. The other bridge is used to operate the motor in reverse and to brake it in forward. Another function that many drives provide is operation in a master-follower mode. The follower drive, or slave drive as it is sometimes called, uses the master drive as the source of the signal that sets its speed or its torque. Usually, any drive equipped for master-follower operation can be used as either the master drive or as the follower drive by simply jumping a set of terminals, by flipping a switch, or by changing a setting at the controller. Most DC drives have adjustments for presetting speed, torque, acceleration, deceleration, and many other operating limits. Many of these settings are programmable by either an outside computer or by a process controller like a programmable logic controller. Some drives can store a control program created by an external controller, so an operation can be carried out even after the external controller has been disconnected from the drive. Finally, most drives have fault indicators. In some cases, this may be only a few lights that verify that the drive is operating correctly. However, many drives have multiple indicators to help identify the nature of the problem when serious faults shut down the motor. Now let's take a close look at some of the common problems that can occur with solid-state DC motor control systems. At the motor, check should be made of the tachometer, encoder, or any other shaft-mounted feedback device to make sure it's mounted firmly. In DC systems, these are often add-on devices rather than an integral part of the motor. Improper alignment or excessive motor shaft in-play can damage the motor coupling and the feedback device and could lead to incorrect feedback. It's also good practice to check for sparking in the motor. Few DC motors run with no sparking at all, black commutation as it's called. But excessive sparking may damage the commutator bar and will wear out the brushes more rapidly. When replacing brushes, adjusting spring tension, and cleaning or reconditioning the commutator bar, the motor manufacturer's recommendations should be followed. Heat can be a major concern with DC motors because they are often operated at low speeds, generating a level of heat which their internal shaft-mounted fans may not be able to dissipate. To help with cooling, most solid-state DC systems include auxiliary external fans. Often, these auxiliary fans are interlocked with the motor, so the motor will not work unless the fan is operating. To help ensure fans are properly dissipating the heat, routine check should be made of the fan and its shroud. All openings and any filters should be kept clean and free of any obstructions that could block the flow of air while the motor is operating. Routine checks should include the motor as well. Because most modern DC motors operate at very high temperatures, it's difficult to tell by touch if they're running too hot. However, the smell of a motor is often a good indication. If it smells hot, it's too hot. Sometimes the load on a DC drive system can cause problems. If the load is too large, it may require more power than the motor can deliver at the speed set on the controller. When this happens, the drive goes into current limit and the motor slows down. The same thing may happen if a normal load is accelerated too rapidly. Extended operation in current limit will eventually cause the controller to trip out. When unexpected, very heavy loads occur, or if a load is suddenly accelerated too quickly, voltage in the field can fluctuate. Many solid-state DC controllers include an adjustable field setting that monitors the field windings. Surges of high armature current from the unexpected heavy load or from the sudden acceleration may create fluctuations in the field that cause the controller to trip out. Problems may also occur if operating voltages are too low or too high. Most controllers will trip out if voltages vary more than 10 to 15% away from rated voltage. However, even if a trip does not occur, low voltage may prevent a DC motor from drawing enough current to operate correctly, and high voltages could burn out components in the controller. Since abrupt changes in voltage may also cause problems, some controllers have a watchdog circuit to monitor disruptions of the electrical supply. These disruptions typically include excessive electrical noise, brownouts, and single phasing in which one or more phases of the three-phase electrical supply are interrupted. Watchdog circuits normally trip out a system and display a fault code. If voltage in all three phases is not equal, that is, if voltages are unbalanced, the controller may be damaged. Over time, unbalanced voltages may burn out a DC controller's bridge rectifiers and may cause intermittent trips from abnormal heating. As a rule, voltage in the highest phase should never be more than 104% of the voltage in the lowest phase. And since large DC drives often include isolation transformers in the circuit, it's also important to check the input and output voltages of the transformer. As in any motor-controlled system, it's also important to make sure that all remote field devices, like limit switches and photosensors, are securely mounted and not damaged, that the wiring is intact, undamaged, and that all the connections are tight, and that the correct signal is being received at the controller. Since tachometers or other feedback devices are an essential part of most solid-state DC systems, malfunctions of these devices will seriously affect operations. All feedback devices should be checked for proper operation. A tachometer, for example, can be checked when a motor is operating at a known speed by comparing its actual voltage output with the voltage it should produce at that speed. In most cases, the place to begin tracking down problems in a solid-state DC control system is at the controller. The fault indications may help identify the most likely causes of operating problems, and the operator's manual may provide suggestions for correcting the problem. If an investigation of any indicated faults does not resolve the problem, take a moment to make sure the settings on the controller are correct for the application. These are often recorded in the operator's manual, or they may be part of the documentation for the system. However, even if the settings do not match, or if any jumpers or switches have been changed, no further changes should be made until it can be determined that the altered settings caused the problem, and then only when you're sure what the correct settings should be. Altering a setting to see if it will fix the problem may only complicate the troubleshooting process and could cause even bigger problems. If a controller has developed an internal problem, it will have to be repaired or replaced. When physically removing a controller, the first step is to perform a proper lockout, including the control of all stored or secondary energy. Make certain all appropriate safety procedures are followed. However, no one should ever attempt any repairs inside a controller unless they have been properly trained. Improper disassembly will almost certainly damage the controller, and improper reassembly could seriously damage the components or other parts of the operation and may cause personal injury when power is applied. In this program, we've looked at the common components of solid-state DC motor control systems, and we've seen how they operate. In addition, we've laid down some guidelines that will help you troubleshoot problems when they occur. Now, while the particular system you'll be working with is operating correctly, make yourself thoroughly familiar with it. If trouble does occur, knowing exactly how the system is supposed to operate will help you get it back online quickly and safely.